Okay, chemistry second year students, this is the last video of the course. In fact, it's a bit of a synoptic situation here. This is 24.5 redox and qualitative analysis, and it brings together several different areas of the course together and tries to tidy up all the redox and transition metals and analysis of inorganic ions. Okay, so let's crack on with it. So I'll share the screen. Okay, so obviously we're going to be doing the chapter 22, chapter 23, 24 tests next week. There are support sessions every Tuesday and Monday, 1 to 2, so come along to those. So obviously you need to try and work through your chapter 23, 24 booklet. 22 should already be finished. Okay, and you should also be doing a past paper a week now, and after Easter we'll be getting down to revision, and you should be doing probably 2 papers a week really. Okay, so if you're in class, you could have done this on whiteboards, but you should have a go at doing this now. Pause and have a go at these questions here. Okay. So here are the answers to those questions. So how do ligands bond to transition metals? They donate a lone pair of electrons to form coordinate bonds or dative bonds with the transition metal ion, so it's a covalent bond. What is the coordination number of cobalt 2+ in the complex ion? We would call that tetrachlorocobalt 2. Okay, it will be 4, okay, because there's 4 chlorines surrounding it. Remember that if you get 4 chlorines into a complex, they tend to force it to become tetrahedral because chlorine is quite a large ion. Okay, AgCl is an insoluble salt that forms a linear complex ion on the addition of ammonia. When have you seen this reaction? I can write an equation for it, where it's a conformation test for chloride ions when you do a silver nitrate test. Okay, so chloride dissolves in ammonia. Okay, so you end up producing the complex ion, which is diamine silver 1 ion. Okay, Ag brackets NH3 2+, and there's the equation on the board there. So you've got the Ag plus ion, which is forced to come out of the precipitate to make the diamine ion. Okay. So we're going to try and look at qualitative analysis of ions. So a lot of this is backing up what we've already done, okay, and looking at this on test tube scale. Also go over the idea of redox and disproportionation reaction of copper, which will tie in with practical 31. Okay, recall the redox reactions and color changes of the Fe2+, Fe3+, and the chromium 3+, chromium or chromium +6 oxidation state in the dichromate ion. Okay, so disproportionation reaction, which we have done before, but just to recap, it is a redox reaction where one specific species is both, or one element, the same element, is both oxidized and reduced in the same reaction, like when copper 2+ reacts with iodide to make copper iodide, which is copper in 1+ state. Sorry, it's the iodide that it changes. So the iodide is -1, it becomes iodine. Okay, and what am I talking about? Okay, we'll come on to that in a bit. Okay, so revision point. Remember any examples? Okay, so chlorine reacting with water is going to give you one of those. So again, have a read of those questions. Okay, and see if you can work out the reaction of chlorine with in those systems. Okay, so pause the video until you've completed this. Okay, so balanced equation of the reaction of chlorine with water. So here we have a disproportionation reaction. The chlorine has gone from 0, okay, to -1 in HCl, and in the chlorate it is now +1. Okay, so hydrogen chlorate, it's chlorate 1. Okay, because we've got oxygen is 2-, hydrogen is +1. The chlorine must also be +1 to make sure that the hydrogen chlorate is 0 overall. Okay, chlorine with cold aqueous sodium hydroxide is also an example. Okay, so again, chlorine, which is 0, becomes chlorate, again +1, and -1 in sodium chloride. So it's +1 in sodium chlorate and -1 in sodium chloride. Okay, at the higher temperatures, react to form chlorate 5 ions instead of chlorate 1. Balance equation for this shows also disproportionation. disproportionation, spelled that wrong there. Okay, so three chlorine molecules react with 6 sodium hydroxide, making sodium chlorate 5 and sodium chloride. Okay, so it's +5 and it's -1. So it started at 0, so it's gone both up and down. Okay, you know, to balance that, here this is how we worked it out. Chlorine needs 2 electrons to make 2 chloride ions. Okay, chlorine plus 12 OH minus is going to make 2 ClO3, okay, plus 10 electrons plus 6 H2O. Okay, therefore disproportionation. Okay, so we've done the manganate reaction with iron. Okay, iron is oxidized to Fe3 plus, iron 2 plus is oxidized to Fe3 plus, and the purple color is decolorized by iron to form a color solution. Now we've then done this as a practical 26. Okay, to analyze the amount of iron in iron tablets. So it's a redox volumetric analysis. Okay, and we've got this electrode potential, and because it's so positive, it's highly likely that the manganate will be, or the manganese in the manganate will be reduced. Okay, and at the end point it goes light pink because basically it's going to react with whatever you're reacting it with, so the purple color disappears until you've reacted everything you're reacting it with. Okay, it needs to be acidified. Okay, and it needs to be sulfuric acid, not hydrochloric acid. Okay, and the key thing is if you have chlorine in the system, that the manganate is powerful enough to oxidize the chlorine to make things like chlorate. Okay, so we can use it to estimate iron, hydrogen peroxide, ethanoic acid, oxalic acid. If you go back to when we talked about ligands, we mentioned ethanoic acid is a decent ligand because it's got 2 carboxylic acid groups. It can make a chloride. It's a bidentate ligand. And we said that its actual name is ox. That comes from its old name. Ethanoic used to be called oxalic acid. So ox is obviously a shortening of that, and that's how, and it's such a common one used to chelate that it is abbreviated to ox. And yeah, the ethanoic ions are what does the chelation. If you do it with oxalic acid and ethanoic ions, okay, if you're going to identify those with, we're going to measure those for volumetric analysis with manganate, it needs to be above 60. And as I said, no indicator is required because as soon as all of the iron or all the peroxide or all the oxalic acid or all the oxalic ions are used up, then the purple color will start to come through, and obviously just a touch of it will make it be light pink at the end, and that's what you're looking for. Okay, so if we have iron 2 and iron 3 plus, iron 3 plus is the orangey brown and the iron 2 is pale green. So that's sort of something to use to identify the difference between an iron 3 compound and an iron 2 compound. So iron 3 compounds tend to be the darker orangey brown type ones, and iron 2 tend to be pale or green. Okay, so it's reduced by iodide ions. Okay, the color of iron 2 is obscured by the brown color of iodine. Okay, so iron 2 is pale green, but iodine, which is made when you react iron 2 plus with iodide, iron 3 plus with iodide, it's the pale green is obscured by the color of the iodine. So how do we know what happens? We can use electrode potential to explain the reactions and why they happen. So you can look up the electrode potentials on page 53 of your booklet for each system. Okay, so you can have a look at those. I'll put those up there in a second. Okay, so the iodide and iodine system is plus 0.54 volts. The iron 3 plus Fe2 plus is 0.77 volts. And the manganate system is, as we said before, plus 1.5 volts or 1.51 volts. And you can see we put the least positive at the top. Okay, so the one at the bottom will be reduced and go in the direction that is written. Okay, so we could take manganate could react with iron 2 plus to make iron 3 plus and Mn2 plus, or manganate could react with iodide to make I2 and Mn2 plus. Okay, we could see that iron 3 plus would react with iodide to make iodine and iron 2 plus. Okay, So all of those things could happen. So that is the anti-clockwise rule in action. So bottom left reacts with top right to make the top left and the bottom right. Okay, and that's if we list the electropotentials with the most positive at the bottom or the least positive at the top. Okay, so so those are the electropotentials. Equilibrium, more likely to gain electrons, shift to the right and undergo reduction. So the more positive, as I just said, yeah. So on your textbook, use your textbook to help you to answer the question 2 on page 32 of your booklet if you haven't already done so. Okay, so do that now. Okay, so we've now come on to the reactions of dichromate and chromium-3. So chromium here is +6, and obviously chromium-3 is +3. And so it again is a good oxidizing agent. It will be reduced to chromium-3+, so +6 to +3, it's reduced. And something like zinc, which is 0 here, is oxidized to 2+. Okay, and you're well aware of this idea of green, it being green and orange in the presence of acid. Okay, and you saw it's actually not in the present. If you haven't got acid, it's a different color, which was what was we went through in the last video. So it's acidified dichromate, okay, which is green, becomes orange, addition of zinc. But if I add more zinc, the chromium-3 can be reduced to chromium-2. Okay, so you should have a go at writing an equation for that. I'm not sure I put a pause section on here, but have a go at writing an equation for that. So you might want to stop now and do that. Okay, so it looks like this. Okay, zinc, you know, plus Cr3+, which is green. Okay, becomes that which is blue, and Zn2+. So yeah, so this is the chromium-3+ when it doesn't have the acid. Okay, so it's pale green, okay, which is what we discussed in the last one. And we said that when there is a lot of acid, it's orange. Okay, so zinc plus chromium-3+ is going to go from green to blue. But if you started with this, it's going to go from green to blue anyway, because you know it will go first. It will do this equation. Okay, so the zinc will be oxidized by this here. Okay. And we, you know, it goes orange. But if there's excess zinc, then it will react with the chromium-3+ to make chromium-2+, which is blue. So we can have a look at the standard reduction potentials or redox potentials to see this. Okay, so hang on, it's going to come up. Here we go. Yeah. So chromium is the highest oxidation state. It's +6 out there. All the substances is going to be an oxidizing agent. It's, you know, we know that it's very widely used. We did it with alcohols and in inorganic chemistry. There's a bit of a tongue twister there. It's used for oxidation. Okay, it can be used as volumetric, but with special indicators, its color change makes the endpoint hard to observe. So we're going from orange to green. Okay, so it's not so good as you know, it doesn't have a self-indicating property like manganate, because you know, orange to green is a bit iffy. Okay, so we need to use special indicators. Okay, so orange becoming green. Okay, its potential is +1.33. Okay, its value is lower than that of chloride. Okay, so that means, yeah, so with the manganate, we couldn't use chloride because, you know, the manganate system was +1.5. It would oxidize the chloride. Okay, so if you had used HCl, it would oxidize, it would affect the manganate reaction. So you can't use hydrochloric acid with manganate. You could do it with dichromate because its electropotential here is just lower than the chlorides. Yeah, so the chloride ions or this system would not affect this because it is lower than that. However, because we use sulfuric acid with the manganate system, we might as well just keep sticking with sulfuric acid with the dichromate system. So our hydrogens come from the sulfuric acid. Okay, we could use hydrochloric, but because we use sulfuric acid with manganate, it seems sensible to continue to use sulfuric acid when we making an acidified solution for oxidation, and where this is the oxidizing agent. Okay, so obviously that is explaining that, or that confirms that there with that value. Okay, so let's have a look at the reactions of it. In the presence of hot alkali, hydrogen peroxide is a powerful oxidation, and it can be used to turn the chromium 3 back to chromium 6. Okay, so the hydrogen peroxide system is more powerful than the chromium system. So here's the chromium system, green. Okay, no hydrogen present, so it is the green color, not the orange color. Okay, and we're doing an alkaline system here. Okay, so hydrogen peroxide reacting to make water. Okay, remember the hydrogen peroxide decomposes naturally to release oxygen. Well, where's this oxygen going? It's being added to the chromium, okay, to make our CrO4 2-, and that is where chromium is back to being +6 again. Okay, and that's a sort of yellowy color. Okay, so that chromium ion is yellow. Okay, and the action of yellow chromate will produce orange. So if we add acid to that, then we get our orange dichromate back. Okay, so we can take our chromium 3+, turn it back into chromium 6, and that's yellow. And then if we acidify this, then we get our dichromate ion. Okay, so dichromate 6 is orange. Okay, chromate is yellow. Okay, and dichromate is stable in acidic solution. Okay, chromate is stable in alkaline solution. Okay, so here in alkali, the dichromate becomes chromate. Okay, so chromium 6, which is yellow, so it goes from orange to yellow. And in acid, the chromate 6, which in the chromate ion becomes dichromate. Okay, because we've added the acid. So that's the sort of interconversion. Okay, so we now can go back to looking at this, and here, we have got the copper system. Okay, so it's redox. Okay, so we've got Cu2+, which is +2, becoming +1. Iodide here is -1. That hasn't changed, so that's -1 to -1. The iodide must change somewhere, otherwise it's not a redox reaction. So the iodide is here -1, but here in the iodine it is 0. So it has been oxidized. So iodide's gone from -1 to 0, and the copper has been reduced +2 to +1. Okay. So we can use it to with thiosulfate. Now that's the back titration, so that again is synoptic. You need to go back to 23.3 to see that. Okay, and then we can use that to analyze the copper, and you'll do that in 31, where you'll be taking brass rivets which contain a certain amount of copper, and you'll be analyzing the copper with the iodide solution, and you're reacting with iodide, and then you do a titration with thiosulfate, which reacts with the iodine. Okay, so when we have another copper 1 oxide, it can react with sulfuric acid. We get a brown precipitate of copper, browny red precipitate of copper. And we also get blue copper sulfate solution. So that is disproportionation. So we've got here +1 becoming 0, and here +2. Okay, so the copper's gone both up and down. Okay, so you can use oxidation numbers to show that. Copper ions have been reduced. Why does this happen? Okay, so let's have a look at the systems involved. So copper 1 is unstable, whereas copper 0, i.e. copper solid, and copper 2 are more stable. And you can see that from these electropotentials here. So copper 2+ can become copper plus here, okay, but copper plus can become copper solid fairly easily with the potential there. And so you can put the two together and work out their electropotentials by combining them. Okay, you end up that copper plus can become copper solid and copper 2+. So it's both been reduced and oxidized in there. So that's a equation for that. And that's what explains why copper 1 is limited, because as soon as you make copper 1, it has the opportunity to be turned back into copper solid. Okay, but we can stabilize it by forming complexes. So that's another role of complexes, which, you know, synoptically goes back to the last lesson. Complexes can stabilize uncommon or less common oxidation numbers of transition metals. Okay, and in fact here we have the iodide stabilizing it. Okay, so we end up with 2 CuI. Okay, and there is the electrode potential for the iodide system again. Okay, so how does that fit with this? Okay, so we've got, take the copper plus, 2 plus. Okay, it is plus 0.15. The iodide system is plus 0.54. Okay, so this is more positive. So iodine can react with copper plus to make copper 2 plus, but it can also react with copper ions, copper solid. So iodine plus copper solid will make Cu plus and iodide. Okay, but the gap is very small, so it's not particularly likely to happen. So it is more likely to go to copper 2 plus. Okay, so qualitative analysis. So again, it's a bit of a recap. I think we've recapped this quite a lot. In 8.3, it's a test for ammonium ions, test for carbonate ions, test for sulfate ions, and the halide ions. Okay, so we should be able to remember those. So if you're in class, you could do this on a whiteboard. You need to describe how you carry out each test, any observation you make, and equations for the reactions. So on your own, you can pause the video until you complete this. Okay, so we'll go through these anion tests. So carbonate ion, okay, is dilute acid, and you see effervescence or bubbles. Try and use the word effervescence, indicating the presence of carbonate. And you should do it this way first, because if you get the carbonate done first, it eliminates it interfering with some of the other tests. Okay, if you do further tests on the same sample, you add the nitric acid until the bubbling stops. There's no more carbonate left. Okay, so there's the equation. H plus carbonate makes H2O plus CO2, your standard carbonate plus acid reaction. So if you are testing for halide ions, okay, which contain chloride, or you're testing for sulfate ions afterwards, don't use sulfuric acid or hydrochloric acid. That's why it's, you know, we always sort of specify nitric acid. Yeah, because we don't actually do any tests for nitrates very well in the course, because one thing is that nitrates tend to be soluble, so that makes them harder to test for. Here is the reaction there. So nitric acid plus sodium carbonate will make sodium nitrate plus water plus CO2, and of course the nitrates are all soluble, and group 1s are all soluble. So that one's the nitrate is going to be soluble, and the nitrate and the sodium basically end up being spectator ions, hence the equation at the top. You could test the CO2 with lime water and it'll turn cloudy. Okay, so that's the equation for that. Carbon dioxide plus calcium hydroxide makes calcium carbonate and water. Okay, so second, you test for sulfate ions. Add a solution of barium ions. So you need to use something where barium is soluble, which is usually a nitrate or a chloride. Again, don't want to necessarily use the chloride because we might be going on to do the halide ion tests afterwards. So solution of barium ions, you get a white precipitate. Barium sulfate is not soluble. Okay, so we'd find that. Then if you were then going to carry on with the same sample, okay, it's going to be a mixture of ions, you could then filter it, and that would remove the barium sulfate, and so you'd just be left with whatever else is in your mixture. You could use barium chloride or barium nitrate, but if tested, as I said, okay, nitrate is best to use. Test would also show white precipitate carbonate ions are present, because barium carbonate is also white precipitate. Hence, we should do the nitric acid test to get bubbles, remove and make sure there's no more bubbles left. Then you've removed any any carbonates that are there, because you don't want to make barium carbonate. Okay, so there's the ionic equation for that. Okay, so barium 2++ sulfate makes barium sulfate solid, and any spectator ions like the nitrate or whatever the sulfate was in, like sodium sulfate. Those are spectator ions, they've been removed. Okay, you would get a white precipitate with barium carbonate as well. Okay, so you have to be careful that you have removed that first. Okay, so the halide ions, we react them with a silver ion. Okay, it's going to have an insoluble precipitate with the chloride, bromide, and iodide. Okay, if silver nitrate, we add nitric acid. Okay, because that will help. Plus, also make sure that we haven't got any other competing ions, and we get silver ions plus chloride ions, making silver chloride white precipitate. Okay, the spectator ions have been removed. Obviously, cream precipitate with bromide, and a yellow precipitate with iodide. So yeah, we haven't. Hopefully, we've got no carbonate or hydroxide ions in there. Okay, because they're often found with halide ions. So yeah, they shouldn't interfere with the precipitate. Because silver hydroxide is a precipitate as well. Silver carbonate and silver sulfate are also white precipitates. That's why we test for them first. Make sure you got rid of those, because otherwise you could confuse them with the chloride reaction. Okay, so that's our test for those. Okay, and then we would confirm, because the cream and the white are similar, the cream and the yellow are similar. So we would then further test with dilute ammonia or concentrated ammonia. Dilute ammonia would dissolve the chloride, and concentrated ammonia would dilute the silver bromide. Silver iodide would not dissolve in either dilute or concentrated. So then we move on to the cation test, so the positive ones. Right, heat together ammonium ions and hydroxide ions, you get ammonia gas. Okay, because you're going to add hydrogen to the hydroxide to make water. Okay, you have to be careful with this one, that you probably best to do it in a boiling tube, because you're going to use moist pH indicator paper, which would be possibly litmus paper, could use a universal indicator. But you don't want to touch that paper to the sides of the tube. So if you use a boiling tube, you can put it at the top, and the ammonia gas should come up, and the ammonia gas will react with the water in the on the damp paper to make hydroxide, and that will make the paper go blue. You can also smell the ammonia. Okay, and you can use dilute sodium hydroxide as your source of hydroxide ions. So ammonium plus hydroxide makes water plus ammonia. And yeah, it smells like urine. Okay, so those are tests that we've done before, and in practical 27 you will be looking at complex metal ions, and you'll be seeing the colors for those. And if you have done that practical by the time you watch this, then you should know the answers to, or should be able to see the answers to these. And most of the time we're going to start by adding sodium hydroxide. It will produce a precipitate of different colors, which you should have filled in the previous lessons table. You've got the colors of the hydroxides are the key ones that you need to learn. And again, we said last time to use flashcards to do that. That's in last lesson. So those tests for those metal ions you can use, and you can see that table with the colors, and you should have done that in the practical. That is it. Okay, so there's work to do there to make sure you're up together with all this stuff. It is a bit of a mishmash to sort of like bring everything together in terms of redox, in terms of inorganic ions, and identifying them, and in terms of redox in like disproportionation. Okay, so hopefully that is what we have covered. Okay, and we've got all those color changes to make sure you go and learn, and the best way is flashcards and repeat, and then practice lots of questions. Thank you. That is it. Goodbye.